In this video, I wanted to talk about multiple reactions. So now you have a reactor and you have, so far we've been analyzing one reaction occurring, but in reality you probably have multiple reactions occurring, and so we need to come up with a way to account for those reactions. And so originally for this video I had thought about going over the algorithm so it's on page 328 in Elements of Chemical Reaction Engineering by Fogler. I have the 4th edition, and it's figure 6-5, and it's called Isothermal Reaction Design Algorithm for Multiple Reactions. And I'm not actually going to go over this in detail because when I started going over it in class, I quickly realized that it's a lot easier to see how this is done from an example instead of from an example problem rather than going over this algorithm. But I do think it's important to look at this because you're basically doing the exact same thing you have been doing with so you have your reactions and you're just doing a mole balance, writing rate laws, doing stoichiometry, adding your pressure drop if you have a pressure drop, and then combining and solving with a ODE solver like Polymath or MATLAB, or if it's possible to solve by hand, doing that. Although with the multiple reactions you're going to end up with multiple ODEs, so you probably want to use a solver to solve those. So I'm not going to go over this, but I highly recommend looking at this algorithm because it summarizes everything pretty nicely, and you end up with a lot of equations for these problems, and it can be easy to get confused. And so if you use a specific algorithm or technique and just step through, it's a lot easier to just go through and say, okay, I need this, now I need this, now I need this, instead of getting confused about what you need. And so for this video, I decided to actually go through example 6-6 and kind of combining that with example 6-5. So in example 6-5, they write rate laws for a multiple reaction, and then in example 6-6, they go through the whole thing. So the mole balances, rate laws, and stoichiometry, and then they combine everything and solve it in Polymath. And so for the first part of this video, I'll go through and show you how to get all the equations, and then for the second part, I'll go through how to solve them in MATLAB. And so anyway, so for example 6-6, and I guess also 6-5, you have so you have a PFR, and you have 3 reactions occurring. So you have, I'll write them right here. So you have 4 NH3 plus 6 NO to 5 N2 plus 6 H2O. You have 2 NO to N2 plus O2, and you have N2 plus 2 O2 to 2 NO2. And then it gives you some rate laws. So for the first one, it gave the rate of disappearance of NO is equal to K 1 NO C NH3 C NO to 1.5. And then for the second one, it gave you the rate of appearance of N2, so R2 N2 is equal to K2 N2 C NO squared. And then also with the way I'm numbering these, so I should go back. So when you have multiple reactions, the very first thing you want to do is number your equations. So this would be 1, 2, 3. So if they're not already numbered, you want to definitely number them. And then when you're writing the rate laws, this first number is the number of the equations. So this is 1, this one's 2. And then the second one is whatever, this could either be a number, letter, whatever you decide to designate it as. So in this case, they're just using the name of the reactant. So this would be NO. And so then for the third one, we have minus R3O2, the rate of disappearance of O2. And so it's 3 for the third equation, and then O2. And then this is equal to K3O2 CN2 CO2 squared. And then another thing to look at is, I mean, hopefully this is already pretty clear by now, but I'm kind of thinking there might be some confusion. If your rate law has a minus sign in front of it, that is designating that this is the rate of disappearance. So this is the rate at which NO is disappearing. And then this one doesn't have a minus sign, so this is positive, so this is designating the rate of appearance of this. So the rate of appearance of N2. And you can see that in this equation N2 is being formed, so that should be the rate of appearance. And then this one is minus, so the rate of disappearance of oxygen. And so then if you wanted to, like, okay, so say this was written as the rate of appearance of NO, like say it was written like this with no minus sign, it's disappearing, and so its rate of appearance would be negative, so then this would be negative because it's disappearing. So just don't get confused by these signs. You should, if it's on this side, it's probably you need a rate of disappearance, and if it's on this side, rate of appearance. And so if it's on this side, it should probably be, you should probably end up with a negative equation. If you have the rate of appearance, it would be negative, but then if it's the rate of disappearance, that would be positive. So just try not to get confused by the signs. It's just nomenclature. And the other thing is, in order to write the rate laws for these, we need to know the rate law for at least one element, so either a reactant or a product for each equation. If these are given, then that work is already done for you, but if they're not given, then you would need to write a rate law for one of the reactants and one of the products for each of these, and you could do that based on the information you have in the problem. I mean, well, if this were real life, you would probably need to run experiments to figure out what to go. So going back to when we were looking at data and we had the, say, concentration versus time, and we were using that to get the rate laws, you could do something like that to get your rate law. But in this case, where we're just looking at these problems, you'll probably be told, oh, it's elementary, or it's first order, or whatever else, and then you can write your rate law. So just wanted to point that out. So anyway, this is what was given. And so the very first thing you want to do when you start these problems is write your mole balances. So I'll do that over here. So mole balances. And so when you're analyzing multiple reactions, you need to write a mole balance for each species. And so, and this is still pretty much the same thing we were doing before, only before when we were writing one equation, we were usually writing it in terms of conversion x. And this time we want to write them in terms of molar flow rates. And So for the first one, and these are what we derived in chapter 1, and so this is, I mean, we've already seen these, we just haven't really used them that much yet. So for NH3, you would have df NH3 over dV is equal to R NH3. And I mean, normally when I'm writing equations like this, I like to go through and say that one's A, B, C, D, and then number the others accordingly. So that would be B, C, E, etc. The only reason I'm not doing that for this problem is because in the book they didn't do that, and so I wanted to kind of do this problem how the book did, so you can go back and look at it. And the only reason I do that is because then it's easier to write than like writing these subscripts every time. So okay, so we have NH3, so we need one for NO, so dFNO over dV is equal to RNO. We need N2, dFN2 dV is equal to RN2. dFH2O dV is equal to RH2O. See, I got NO, N2, need O2. So dFO2 dV is equal to RO2, and then NO2. So dFNO2 dV is equal to RNO2. So this is your mole balances for this series of reactions. And just to be clear, we're doing the PFR, so we're using the mole balances for a PFR. But if you had, say, a batch or a PBR or a CSTR, then you would use the mole balances for those reactors. So let's see. So, and also this is why by now, hopefully you're using some kind of solver to solve your equations, because in this case you end up with 6 coupled ODEs, and you're going to have to solve that numerically. So next I want to write the rate laws, and I'm just going to erase everything except for these equations. Okay, so we've done the mole balance. So check that off. And next we want to write rate laws. And so if you remember, we were already given the rate law for one of the reactants in each of these. And so what we need to do is just go through, and so I'll just write that down real quick. So we were given minus R1NO for this one. We were given R2N2 for this one. And we were given minus R3O2 for this one. So writing the rate laws, I think that this is the part where you can get really confused. And so if you go through in an ordered way and write your rate laws, then this should be pretty straightforward. It's not hard, it's just that you end up with a lot of equations and it can get confusing. So just approach it in a really ordered manner. So what I usually do is, so you need to write a rate law for each. Well, so we need to, so we eventually need a total rate law for each one. So we'll have so if you remember the mole balances which I erased. You had, say, dFNH3, dV is equal to the rate, so RNH3. So you need a RNH3 that's, some people call it R net, so it would be so it would account for what's happening with NH3 in all of these equations. And in this case, it's only in the first one, but for some of these, like we have NO in 2 of them, we have oxygen in 2 of them. So this is NO. So you need to account, in your total rate law, you need to account for that through all the equations. So what you can do is just start kind of summing these, I guess. So we know RNH3 is equal to R1 NH3. And we know that since NH3 isn't in the second or third reaction, that this is what it is. But some people will just write an equation, they'll just write it in for all of them. So RNH3 plus R3, NH3. And then you know that these are 0. And so you can just write, I mean, you can write this either way. I think if you write the whole thing, it's it's easier to not get confused because you're definitely accounting for everything, but it takes more time. So if you just look at it and see, okay, it's only in the first one, then I know I only need that. So then, for instance, the second one, RNO is equal to R1 NO plus R2 NO. So we know it's in the first one and the second one. And then we could continue and write R3 NO and just say that's 0. So you can kind of see how you would do this for each of them. And for every single one, you could write, so for the next one, N2 is in all of them, so R N2 is equal to R1 N2 plus R2 N2 plus R3 N2. And then R H2O is equal to R1 H2O, because we only have water in the first reaction, and so yeah, you just continue doing that with all of these. So let's see, so RO2 is equal to R2 O2 plus R3O2, because oxygen is only in the second and third one, and then RNO2 is equal to R3NO2, because we only have NO2 in the third reaction. So then once you have these, you need to figure out what each of these individual parts are. So you need to figure out what, well, we already know, I believe, actually we don't know that. So we need to figure out what R1 NH3 is. We need to figure out what R1 NO is, and R2 NO is, and R1 N2. So we need to figure out what all these are. And we should have everything we need because we have, it's already given us a rate for one of the reactants for each reaction. And that's all you need is one. And the reason why is because if you remember this formula, if you remember RIA over minus AI is equal to RIB over minus BI is equal to RIC over CI is equal to RID over CI. And I'm pretty sure this was in chapter 3, but so this is just stoichiometry, so that should be pretty clear. So then I think the easiest way to do this is to just go by reactions. So I'm going to erase some stuff real quick and then show you how I do this. So I like to go by reactions. So this is reaction 1. And using this formula, we know that R R1 NH3 over minus 4 is equal to R1 NO over minus 6, and this is the one that was given, is equal to R1 N2 over 5 is equal to R1 H2O over 6. So then using this, since we know what R1 NO is, we should be able to get all the others. So for instance, the rate of disappearance of R1 NH3 is equal to, so we multiply the 4 over, so 4 over 6 R1 NO. And so we know that that's 2/3 R1 NO. So then we just plug in the R1 NO, which we know, and then we know what this is. And then in this particular case, well, I'll just go through them real quick and then combine them. So we know that R1 N2, that's the rate of appearance of R1 N2, is equal to, so we multiply the 5 over, so we end up with 5, 6, R1 NO. And then same thing with R1 H2O is equal to, and then we just multiply the 6 over, and so we end up with R1 NO. And then we can do the same thing for reaction 2. So if you do that, we have R NO over minus 2 is equal to R N2 over 1 is equal to R O2 over 1. And I'm just going to erase this real quick. We just do the exact same thing. We know what, I forgot to put 2's on these. That's what I mean, like you need to be really careful, because this is where you can get confused, like if you forget to put in the numbers for your equations. So like with this, if I hadn't have noticed that I forgot to put this 2 in, then this is actually something different, because Rn2 is not the same as R2N2. So just be really careful with this. So then we know what R2N2 is, so we can do the same thing. So we know that the rate of disappearance of R2NO is equal to, multiply the 1 over, so 1/2 R, wait, is that right? Actually, sorry, I'm multiplying the 2 over here, so 2 R2N2. And then this, we can do the same thing for R2O2, and that's the rate of appearance because it's on this side. So just multiply the 2 over again, and we get 2 R2O2. And then just doing the exact same thing for reaction 3. And this can seem really tedious, but I can guarantee if you go through each step and write down your stuff clearly, this is going to be a lot easier than if you try and skip steps, because if you try and skip steps, you're likely to get confused. So, okay, so for this one, you have R3N2 over 1 is equal to R3O2, oh, and these are minus 1 and minus 2, is equal to R2 R3NO2 over 2. And so then doing the same thing, we know what R3O2 is. We know what this is. So then we can get the rate of disappearance of R3N2 is equal to, well, so just multiply the 2 over. So we want to multiply the 1 over, so 1/2 R3O2, and the rate of appearance of NO2 in 3 is equal to, and so we multiply the 2 over, so we just get R, so 2 divided by 2 is 1, so we just get R3O2. I'm going to erase this. So at this point, what we would do is combine the rates and to get the total rate loss. So you remember the equations we wrote where we said RNH3 is equal to R1NH3, RNO is equal to R1NO plus R2NO, etc. So now we want to take all these and just plug them into those so we get the total or the net rate law. So for the first one we had RNH3 is equal to R1NH3, and we know that that was 2/3 R1NO. This is the rate of disappearance. And so that was equal to 2/3 K1NO CNH3 CNO to the 1.5. And then we know that RNO is equal to R1NO plus R2NO. And so R1NO was given, and so that was K1NO CNH3 CNO 1.5 plus, and then R2NO was 2 K2N2 CNO squared. Rn2 was equal to R1N2 plus R2N2 plus R3N2. And I'm not going to continue writing all of these down, but you can see where I'm going. So we had derived, so first of all we know what R2N2 is, and then we had derived R1N2, which was 5/6 R1NO, and then this was plus R2N2, which was given, and then R3N2 was, let's see, where was that? 1/2 R3O2. So then R2N2 is known, and R3O2 is known, so, and R1NO, so you would just plug these in. And same thing for RH2O is equal to, let's see, that was R1H2O, which was R1NO. And then we had RO2 was equal to R2O2 plus R3O2. And we know that R2O2 was, so this was equal to R2N2, which is known, plus R3O2, which is known. So now you can just plug these into here and you know the rate for O2. And RNO2 was equal to R3NO2, which was just R3O2. So that should be it for the rate laws. And you'll see when I get to the programming part, kind of what you, so like when I program this, I'm not going to retype all of this each time. I'll write these as variables, so R10 is equal to this, R2N2 is equal to this, R3O2 is equal to this. And then when I type these equations, I'll put these in terms of these. So RO2 is equal to R2N2 plus R3O2. Same thing with this one, RN2 is equal to 5/6 R1NO plus R2N2 plus 1/2 R3O2. So I'm not going to rewrite all of this each time. But it's good just to kind of see how these equations work together. So I'm going to erase some stuff real quick and then do the stoichiometry. So the next step is the stoichiometry. This is gas phase, so we need to use this equation, Cj is equal to Ct naught P over P naught T naught over T. And just so you can kind of, sometimes it helps me to see equations together so I can see what the difference is. So if this were liquid, you would use Cj is equal to Fj over V naught. So this is liquid. This is gas. So we're using gas because this is a gas reaction, and so there's no pressure drop, so P equals P naught, so this is equal to 1. It's also isothermal, so that's 1. So then we just have, oh, and I missed this, Fj over Ft. So Cj is equal to Ct naught Fj over Ft. And then this is how this relates what we have in the rate law, because we have concentrations in the rate law, and this relates that to the molar flow rates, which we have in the mole balance. You can kind of see where I'm going. You would need to write this for each one. So Ca is equal to Ct naught Fa over Ft. Cb is equal to Ct naught Fb over Ft. Cc is equal to Ct naught Fc over Ft. So you write that for all of them. And then you need an equation for Ft. So Ft is the sum of all the molar flow rates. So that would be FNO. Oh, and sorry, I kind of switched to A and B. These are, I'm so used to working in A and B. These would be like, this would be NH3, NH3, NO, NO, N2, N2, etc. So then you would have, for total, you have FNO plus F NH3 plus F N2 plus F H2O plus F O2 plus F NO2. And if you So it's the stoichiometry, and the last step is combine. Somebody erase some stuff real quick. Going back to the mole balances, we could technically combine everything. We could combine the stoichiometry into the rate law, and then the rate law into the mole balance. So for instance, for NH3 you would have dF NH3 over dV is equal to R NH3, and so that was equal to minus 2/3 K1NO C NH3 CNO to the 1.5, and then plugging in the stoichiometry, that would be minus 2/3 K1 NO CT naught F NH3 over FT CT naught 1.5 FNO over FT to 1.5. And for D, I'm not going to do all of these, I'm just doing a couple so you can kind of see this. So dF H2O over dV is equal to R H2O. And combining all the equations we just derived, that would be KNO C2O 2.5 F NH3 over FT FNO over FT to 1.5. You could combine this a little more too, so you could combine the CT naughts, so you have minus 2/3 K1 NO CT naught to the 2.5 F NH3 over FT F NO over FT to 1.5. So you can kind of quickly see why you need a solver to solve these equations. And I'm not going to write down the others, but you could go through and do that with all of them. And if you have this book, these are all summarized on page 337 and 338. But what I want to show you real quick, because next I'm going to move to MATLAB to solve these equations, and so I want to show you, in case you're not using MATLAB, you might be using Polymath, I want to show you the equations, like the actual equation that I put in the solver, because I'm not putting this in, so I'll just erase some stuff real quick and show you that summary. For the final part of this problem, I'm going to be solving this in MATLAB, but you could also put these equations into Polymath. So I just went through and summarized everything we derived in the problem and put them in the form, I wrote them in the form of how I'll actually enter them into the computer program. So these are the mole balances. So we have dFNH3 dV equals R NH3, and we have that for each species. And theoretically you could also enter, so I have R NH3 equals R1 NH3, so theoretically you could put dF NH3 dV is equal to R1 NH3, and for this one you could put dF NO dV is equal to R1 NO plus R2 NO. But I like to enter the equations like this because I feel like it's less easy to get confused, plus the computer will calculate all these for you. And so anyway, these are the mole balances, and then I would enter in, and I believe in Polymath, usually you put your differential equations first and then everything else. But in MATLAB, you would actually probably need to put your constants first, and these are the constants that were given. And then you would need to put in your, well, probably these definitions, and then these, and then these. Otherwise you're going to get an error and it'll tell you things are undefined or not declared or whatever. So anyway, so So yeah, so these are your mole balances, and then these are your rate laws. So we know that RNH3 was equal to R1NH3, RNO was equal to R1NO plus R2NO, and etc. for the rest of these. And then as far as defining what these individual things were, we already know that we were given R1NO, R2N2, and R3O2. But I want to point out a few things on the signs for these when you actually enter these into the program. So if you remember, R1NO is given as a rate of disappearance. So it was actually given as negative R1NO. But you put it in the program as the rate of appearance, so then this has to be negative. And the same thing with R3O2. And so then you just define the rest of these. So we know that R1NH3 was equal to 2/3 R1NO. R1N2 was equal to negative 5/6 R1NO. And so then we just go through all these. And I just want to talk about the signs real quick. So you want to make sure, like after I put everything into my program, I usually go through and just double check all the signs. So for instance, if you, let's see, is there room to write it? I'd kind of like to write the actual reaction that we're solving. So this was 4NH3 plus 6NO to 5N2 plus 6H2O. For number 2, we had 2NO to N2 plus O2. And for 3, we had N2 plus 2O2 to 2NO2. So then looking at these, we know that NH3 should be the rate of disappearance because it's disappearing in reaction 1. And so we know that if we write it as the rate of appearance, which we are, then it should be negative. So then we just go to here, RNH3 is equal to 2/3 R1NO, and R1NO is negative already, so then this ends up being negative. So we know that that's right. And then RNO is equal to R1NO plus R2NO, and so in the first one, well, it looks like it's disappearing in both of them. So we know that both of these should come out negative. And we already know that R1NO is negative because it's given. And then R2NO was minus 2 R2N2, and R2N2 is positive, so then that'll end up being negative as well. So that's right. And then we can do the same thing for N2, only this one is appearing in the first one and the third one, and disappearing in the second one. So the R1N2 and R3N2 should end up being negative, and R2N2 should be positive. So R1N2 is minus R1N2 minus 5/6 multiplied by R1NO, and that, let's see, yeah, so that ends up being positive because it's negative multiplied by a negative. So that's right. R2N2. Sorry, I think I said that it was supposed to be negative, so it should be positive. So it's appearing in reaction 1 and reaction 2. So it should be positive in them, and then it should be negative in the third one because it's disappearing. So yeah, that's right that this is positive. R2N2 is given as positive, so that's right. And then R3N2 is 1/2 multiplied by R3O2, which is negative, so that ends up being negative. So that's right. So RH2O is appearing in the first reaction only, so R1H2O should be positive. And if we go here, it's negative negative 1 multiplied by R1 NO. So negative multiplied by negative is positive. So that's right. O2 is appearing in the first reaction and disappearing in the second one. So R2, O2 should be positive in the first and negative in the second. So see, R2O2 is equal to R2N2, which is positive. So that's right. R3O2 is, see, oh, it's given and it's negative, so that's right. And then RNO2 is equal to, so NO2 is appearing in the third reaction only, so that should be positive. And so RNO2 is equal to R3NO2, which was equal to negative 3O2, so negative multiplied by negative is positive, so that one's right. So I feel like that's just a good thing to go through and double check that all your signs are right, because I think with writing the rates, it's really easy to get the signs messed up. And then we need to write, so if we look at the rate laws that we have, because they're all in terms of these three, then we know that we need concentrations for NH3, for NO, for N2, and for CO2. So, and that was this equation for a gas, and then we just have our constants, and we should have everything we need to solve this. So in the next video I'm going to go through this in MATLAB.